Hi students, how are you? Hope you are all fine. Today's my lecture is on Carnot cycle. You know it's a very important task of thermodynamics. Sydur Carnot first proposed this heat engine procedure to show that the efficiency is based upon the temperature it operated. So, what is Carnot cycle? The cycle of processes which occurred under reversible conditions is referred to as Carnot cycle. Carnot cycle comprises of four operations. First one is isothermal reversible expansion. Next, adiabatic reversible expansion. Third one is isothermal reversible compression. And the last one is adiabatic reversible compression. So, before starting the study of Carnot cycle, we have to remind some basic ideas of thermodynamics. First, we have to remind thermodynamic reversible process, and next isothermal process, then adiabatic process, and finally first law of chemical thermodynamics. So, what is thermodynamic reversible process? The process which takes place very slowly and its direction at any point can be reversed by any change in the state is called thermodynamic reversible process. And what is isothermal process? Isothermal process is that in which the temperature remains fixed. And what is adiabatic process? Adiabatic process is that where no heat can flow into or out of the system. And finally, we have to know first law of chemical thermodynamics. What is the first law? The total energy of an isolated system must remain constant, though it may change from one form to another. And this is actually commonly known as the first law of chemical thermodynamics. And this is the mathematical expression of the first law of chemical thermodynamics. Here we can see that del E is equal to Q minus W, where del E expresses the difference of energy and Q expresses the transferred heat and W expresses the work done by the system. Let's consider a gas enclosed in a cylinder that placed in a reservoir at temperature T2, and the initial pressure and volume of the gas is considered P1 and V1, and now the gas is allowed to expand isothermally from A to B, and by this expansion we get Q2 is equal to W1, where Q2 is considered as the absorbed heat of the system, and this Q2 is equal to W1 comes from the first law of chemical thermodynamics. We know del E is equal to Q minus W according to the first law of chemical thermodynamics, and as the process is isothermal, so del E is equal to 0, so Q2 is equal to W1. But we also know from the isothermal reversible expansion of an ideal gas, W1, that is work done by the system, is equal to RT2 ln V2 by V1. So, by substituting the value of W1 by Q2, we get Q2 is equal to RT2 ln V2 by V1. The second operation is adiabatic reversible expansion, where the gas goes from the point B to C, and here the temperature drops from T2 to T1, and this adiabatic reversible expansion gives us the equation del E is equal to minus W2. And how it comes? It also comes from the first law of chemical thermodynamics, where Q is equal to 0 because the process is now running adiabatically. So W2 is equal to minus del E, but we know del E is equal to CV T1 minus T2 according to the adiabatic reversible expansion of an ideal gas. So W2 is equal to CV T2 minus T1, and here W2 is also the work done by the system. The third operation is compression, and here we can see here that the system is now go to D point from the point C, and according to this isothermal reversible compression, we get the equation minus Q1 is equal to minus W3, and here minus sign indicates that the heat released to the reservoir by the system, and minus W3 indicates that the work is done on the system. So minus Q1 is equal to minus W3 is equal to RT1 ln V4 by V3. And the fourth operation is adiabatic reversible compression, and here we get minus W4 is equal to minus CV T2 minus T1, and here also W4 indicates that work which is done on the system. So the ultimate or net work done in one Carnot cycle is equal to W, which is W1 plus W2 plus W plus minus W3 plus minus W4. If we substitute the value of W, then we get RT2 ln V2 by V1 plus CV T2 minus T1 plus RT1 ln V4 by V3 minus CV T2 minus T1. And here it is dilated, and W is equal to RT2 ln V2 by V1 plus RT1 ln V4 by V3 is ultimately find out. So the net work done by one Carnot cycle, W is equal to RT2 ln V2 by V1 plus RT1 ln V4 by V3, and that's the overall work done by one Carnot cycle. Now I want to derive another expression of the total work done by one Carnot cycle, that is W is equal to R T2 minus T1 ln V2 by V1. Our previous expression was W is equal to R T2 ln V2 by V1 plus R T1 ln V4 by V3. That is simplified to W is equal to R T2 ln V2 by V1 minus R T1 ln V3 by V4. So to derive this expression of W, we have to start from the first operation of Carnot cycle. From the first operation, we get Q2 is equal to RT2 ln V2 by V1, and from the third operation we get minus Q1 is equal to RT1 ln V4 by V3, or Q1 is equal to minus RT1 ln V4 by V3. So the net heat absorbed by one cycle, Q is equal to Q2 minus Q1 is equal to RT2 ln V2 by V1 minus RT1 ln V4 by V3, or Q is equal to RT2 ln V2 by V1 minus RT1 ln V3 by V4. According to the adiabatic process, here we can see that this transformation of B to C and D to A is adiabatic, and according to adiabatic process we know T2 by T1 is equal to V3 by V2 to the power gamma minus 1 for thermodynamic expansion. This is thermodynamic expansion, and for thermodynamic compression, this D to A transformation is thermodynamic compression, and for thermodynamic compression we know T1 by T2 is equal to V1 by V4 to the power gamma minus 1, or T2 by T1 is equal to V4 by V1 to the power gamma minus 1. So by solving 1 and 2, these two equations, we get V3 by V2 is equal to V4 by V1, or V3 by V4 is equal to V2 by V1. So by putting the value of V3 by V4 in this expression of W, we get W is equal to RT2 ln V2 by V1 minus RT1 ln V2 by V1 in the place of V3 by V4. So the new expression of W is equal to RT2 minus T1 ln V2 by V1. Now, if we want to find out the ultimate efficiency of a Carnot cycle, then we have to use these two equations. One equation is for W is equal to RT2 minus T1 ln V2 by V1 that expresses the net work done by a Carnot cycle, and another equation is Q2 is equal to RT2 ln V2 by V1 that expresses the total heat absorbed by a Carnot cycle. So the thermodynamic efficiency of a Carnot cycle, that is expressed as eta, and this eta is equal to W by Q2, that is RT2 minus T1 ln V2 by V1 divided by RT2 ln V2 by V1. And by solving this problem, we get eta is equal to T2 minus T1 by T2. And this is the ultimate expression of thermodynamic efficiency of a Carnot cycle.